From the vastness of the space between the stars, a celestial body moves silently toward our planetary neighborhood. Scientists observing the sky detect its presence, another traveler from a distant solar system. But this time, something powerfully draws their attention. This object is not traveling alone. Thousands of small pieces escort it, forming a cloud reminiscent of insects following their leader through the void of the cosmos. We are facing a comet from interstellar space, accompanied by 10,000 objects. Could it be possible that this is not simply a natural event? Are we perhaps witnessing something that has never been recorded in all the years of astronomical observation? Consider for a moment that each and every one of these 10,000 bodies carries data. Inscriptions engraved on their surfaces by some extinct civilization from geological eras long past. Perhaps it is a consequence of a cosmic-scale catastrophe that completely destroyed a planet, scattering it into countless fragments that now travel through the universe as silent witnesses to a tragedy that occurred millions of years ago. Or perhaps, and this is even more disturbing, these bodies are technological artifacts, small probes created to disperse and examine every corner of the Milky Way. Tonight, we will dive into the fascinating story of the interstellar comet 3I Atlas and the impressive cloud of objects that travel with it, an astronomical enigma that tests everything we thought we understood about the cosmos and forces us to rethink our ideas about how celestial bodies form and evolve. If you're enjoying this content, don't forget to subscribe to the channel and leave your comment about what you think of this incredible discovery. On September 20th, 2024, the network of robotic telescopes known as ATLAS, the Asteroid Terrestrial Impact Last Alert System, identified an unusual body moving rapidly through the night sky. At first, it was classified as an asteroid passing near Earth, but a detailed study of its trajectory revealed something truly surprising. This object followed a hyperbolic path with an eccentricity greater than 1, the unmistakable sign that it comes from interstellar space. It was given the designation 3I Atlas, becoming the third confirmed interstellar visitor after 1I Oumuamua and 2I Borisov. What made 3I Atlas a truly revolutionary discovery was not only its interstellar origin, but also what researchers from the Harvard-Smithsonian Center for Astrophysics found when they directed the MMT Observatory in Arizona toward this object. High-definition photographs showed something unexpected. It was not a solitary body, but a central cometary nucleus surrounded by a multitude of smaller fragments. Subsequent studies using the James Webb Space Telescope and the planetary network of radio telescopes confirmed the unimaginable. About 10,000 distinct objects, ranging in size from several meters to microscopic particles like grains of sand, all moving along remarkably similar trajectories. Comets that break apart are nothing new to those who study space. Comet Shoemaker-Levy 9 fragmented spectacularly before crashing into Jupiter in 1994, while Comet 73P/Schwarzmann-Watchman 3 split into more than 60 fragments during its approach to the Sun in 2006. However, these events involved comets born in our own solar neighborhood, specifically from the Kuiper Belt or the Oort cloud. The fragmentation of interstellar visitors is a completely new phenomenon. Oumuamua, the first verified interstellar visitor, was a unique object with enigmatic physical characteristics. 2I Borisov, though clearly identified as a comet, also showed no signs of major fragmentation during its passage through our system. 3I Atlas, with its enormous entourage of fragments, indicates physical processes never before observed in interstellar objects, questioning existing models of how they form and evolve. The central nucleus of 3I Atlas has an approximate diameter of 800 meters, considerably larger than Oumuamua, though smaller than Borisov. Its speed relative to the Sun reaches 27 kilometers per second, confirming without a doubt its origin outside our solar system. Spectroscopic studies show a composition rich in volatile substances, such as water, carbon monoxide, carbon dioxide, and hydrogen cyanide, similar to local comets, but with notably different isotopic ratios. The accompanying cloud extends in an elliptical zone of about 120,000 kilometers, with varying densities suggesting several different fragmentation events. The relative velocity between the fragments is surprisingly low, less than 1 meter per second, indicating that the fragmentation occurred a long time ago or through an extraordinarily gentle process. This is another feature that defies traditional explanations. Detailed observations of the main nucleus of 3I Atlas have revealed fascinating features that distinguish it from other comets studied before. Its surface shows signs of moderate but continuous cometary activity, with various jets of gas and dust emerging from specific areas. Unlike comets originating in our system, which generally increase their activity dramatically as they approach the Sun, 3I Atlas maintains a relatively constant level of outgassing even when it is far from the Sun. Data from the James Webb Space Telescope have made it possible to map the temperature distribution on the comet's surface, revealing anomalies that point to a heterogeneous internal structure. Certain areas show much higher temperatures than expected, possibly indicating the presence of compounds that release heat or an unusual thermal conductivity. The rotation of the nucleus, calculated at 7 hours and 13 minutes, is strikingly fast for a body of its size, suggesting that it may have experienced events that accelerated its angular momentum. Infrared spectroscopy has identified the presence of complex organic compounds, including molecules that are precursors to amino acids such as formamide and acetaldehyde. Even more intriguing is that the isotopic ratios of hydrogen, carbon, and nitrogen are significantly different from those observed in comets of the solar system, providing solid chemical evidence of its origin in a different stellar system with a distinct evolutionary history. The structure of the dust expelled by 3I Atlas also shows peculiarities. Polarimetric analyses indicate mostly elongated particles with optical properties that suggest highly ordered crystalline materials, possibly formed by condensation processes different from those that operated in the primitive solar nebula. The distribution of particle sizes is also unusual, with a notable absence of grains in the 10 to 100 micrometer range, the most common size in comets of the solar system. Radar observations have provided limited but valuable information about the density of the nucleus, estimated at approximately 0.4 grams per cubic centimeter. This value, considerably lower than the density of water, indicates an extremely porous internal structure, possibly with large empty cavities, or an architecture similar to a loose aggregate of smaller fragments weakly bound by self-gravity. When we consider all these characteristics together, an image emerges of an object that has lived a cosmic history radically different from that of local comets. Its structure, composition, and behavior tell the story of a world that formed around another star under physical and chemical conditions that may have been very different from those that gave rise to our own planetary system. What if 3I Atlas were not really a comet in the conventional sense? What if we were observing a fragment of the crust of a larger body, perhaps a planetesimal, or even a planet torn apart by extreme gravitational forces? What if its peculiar structure? The most puzzling aspect of 3I Atlas is not the comet itself, but the extraordinary cloud of objects accompanying it. Detailed observations using multiple ground and space-based telescopes have confirmed the existence of approximately 10,000 distinct bodies following extremely similar paths. These objects range in size from fragments several meters across to microscopic particles, creating a cosmic trail without precedent among interstellar objects. Orbital dynamics studies show that these fragments move in a remarkably stable formation. The relative velocities between components of the cloud are extraordinarily low, typically less than 1 meter per second, a value that contradicts expectations for fragments produced by a violent explosion or catastrophic collision. This kinematic coherence indicates that the fragmentation occurred long ago, allowing dynamic disturbances to gradually dissipate, or that the fragmentation mechanism itself was exceptionally gentle. The spatial distribution of the cloud is also revealing. Instead of homogeneous dispersion, the fragments are organized into distinct families with slightly different orbital properties. Astronomers have identified at least 7 of these main groups, each possibly representing an independent fragmentation event or different regions of the original body. Some groups show a higher concentration of fragments toward the center, while others display more elongated or even toroidal structures. Spectroscopic analysis, although limited by the small size of most fragments, has provided intriguing information. The larger fragments exhibit chemical signatures remarkably similar to those of the main nucleus, suggesting a shared origin. However, some groups show subtle differences in their spectra, potentially indicating compositional variations in the original body or chemical alterations that occurred after fragmentation. Particularly interesting is the behavior of certain fragments that display signs of their own cometary activity, with tiny commi and tails detectable in high-resolution observations. This indicates that even small fragments contain significant reserves of volatile materials and have preserved their structural integrity over an interstellar journey of unknown, but presumably immense duration. When we consider the statistical improbability of this phenomenon, fundamental questions arise about the mechanisms that could produce such an extensive and coherent cloud. Traditional models of cometary fragmentation based on thermal or rotational stress can hardly explain the scale and characteristics observed in the 3I Atlas cloud. What if we are witnessing the consequences of a completely new phenomenon in cometary physics? What if the original body experienced a kind of resonant fragmentation, in which a natural frequency of the object resonated with some external force, causing an orderly rather than chaotic disintegration? What if the cloud were not the result of fragmentation at all, but of an interrupted accretion process? Could we be observing the components of a planetary object that began to form but never completed its evolution into a unified body? What if the patterns in the spatial distribution of the cloud contain information about the history of its parent system, like ripples in a pond revealing the nature of the disturbance that created them? Nevertheless, current observations indicate that the most likely explanation remains some form of fragmentation process, though possibly involving physical mechanisms not previously observed in the context of the solar system. The orbital coherence of the cloud strongly suggests a common origin, and the compositional similarities among fragments point to an original body that underwent multiple episodes of fragmentation before or during its interstellar journey. Reconstructing the trajectory of 3I Atlas has represented an extraordinary challenge for astronomers, requiring advanced computational techniques and international collaboration. Tracing back the hyperbolic orbit of this interstellar visitor reveals crucial information about its origin and its long journey through the interstellar void. Precise orbital analyses indicate that 3I Atlas comes roughly from the direction of the constellation Cetus, with coordinates of right ascension and declination being continuously refined as more observational data accumulate. This trajectory does not point directly toward any known nearby star, suggesting an extremely long journey or significant perturbations during its interstellar passage. Computational models that incorporate the gravitational effects of nearby stars, molecular clouds, and the large-scale galactic structure indicate that 3I Atlas may have been traveling through interstellar space for a period between 10 and 50 million years. During this time, it would have covered a distance of at least 15 parsecs, nearly 50 light-years, constantly exposed to cosmic radiation and the subtle yet cumulative gravitational influences of galactic structures. The asymptotic velocity of 3I Atlas relative to the local standard of rest is approximately 26 kilometers per second, significantly higher than the typical velocity dispersion of young stars, but lower than that of very old ones. This value provides clues about the age and type of the parent stellar system, suggesting a star of intermediate age. Possibly similar to the Sun, particularly intriguing is the coherence of the cloud along this vast journey. Dynamic simulations indicate that even small initial velocity differences should have caused significant dispersion of the cloud during a trip spanning millions of years. The persistence of this cohesive structure suggests that fragmentation may have occurred relatively recently in astronomical terms, perhaps during a close encounter with another celestial body, or due to internal processes triggered during the voyage. Leave a like if you find this cosmic mystery fascinating, and tell us in the comments which theory seems most plausible to you. Analysis of slight differences in the trajectories of various components of the cloud has allowed astronomers to identify several possible fragmentation events, the most recent of which occurred about 25,000 years ago. This timeline offers a fascinating window into the evolutionary history of the object throughout its interstellar odyssey. When we consider the immense distances and time scales involved, our understanding necessarily becomes speculative. The journey of 3I Atlas represents a continuous thread through space and time, linking our solar system with another distant stellar system, possibly one that no longer exists in the same form as when expelled as cosmic traveler. What if we could use 3I Atlas as a probe with the interstellar medium, reading in its surface features and the composition of its coma the cumulative effects of millions of years of exposure to interstellar gas, dust, and radiation? What might it tell us about the regions of space it has crossed? And what if the fragmentation patterns we observe are a result of multiple encounters with molecular clouds or interstellar magnetic fields, each leaving a distinctive imprint on the cloud structure? Could the cloud contain, encoded in its spatial distribution, a history of interstellar travel more detailed than any human instrument could record? And what if, in the distant future, objects from our own solar system, ejected by planetary or stellar perturbations, were to reach other stellar systems, carry with them the chemical evidence of Earth and its biosphere? What might hypothetical alien astronomers conclude about our world? Nevertheless, current observations indicate that regardless of its specific origin, 3I Atlas represents an extraordinary messenger from another planetary system, a carrier of information about the processes of star and planet formation in a different region of our galaxy. Its hyperbolic trajectory definitively confirms its interstellar nature, establishing it as part of a population of objects that travel between the stars, physically connecting systems separated by vast distances. Identifying a specific stellar system where 3I Atlas originated represents one of the greatest astronomical challenges. Unlike comets in our solar system, whose orbits can be traced back to the Oort cloud or the Kuiper belt, interstellar objects come from distant stellar systems, and gravitational perturbations during their interstellar journey greatly complicate precise tracking of their origin. Astronomers have employed sophisticated probabilistic techniques, combining the reconstructed trajectory of 3I Atlas with extensive stellar catalogs, such as those from the European Space Agency's Gaia satellite. This analysis identifies several candidate stars that could have been the comet's original home, though all such identifications carry significant uncertainties due to the inherent limitations of reconstructing trajectories over millions of years. The most promising candidate is a K-type star approximately 47 light-years away in the constellation Eridanus. This star, with roughly 0.8 solar masses, has an estimated age of 3 billion years and shows spectroscopic evidence of a substantial debris disk system, indicative of significant planetary activity. However, the statistical probability that it is truly the birthplace of 3I Atlas is estimated at only about 20%. Planetary formation simulations in systems similar to this candidate suggest favorable conditions for the formation of numerous cometary bodies in regions analogous to our own Kuiper belt. Particularly interesting is the presence of a giant planet detected through radial velocity measurements, whose gravitational perturbations could have efficiently ejected cometary material into interstellar space. Isotopic analyses of the volatile material emitted by 3I Atlas provide additional clues about its natal system. The ratios of deuterium to hydrogen and nitrogen, 15 to nitrogen, 14 are consistent with formation in a protoplanetary disk warmer than the region where our system's comets formed, possibly closer to its parent star or around a hotter star altogether. When we consider the fundamental limitations of our ability to trace objects across geological timescales and interstellar distances, we must acknowledge that any identification of the parent star remains within the realm of probability, not certainty. 3I Atlas reaches us as a message in a cosmic bottle, but the identity of the sender remains unknown. What if 3I Atlas came from a system that no longer exists? What if its parent star had already completed its evolutionary cycle, expanding into a red giant or even exploding as a supernova after the comet's ejection? The object we observe could be a fossil remnant of an extinct planetary system. And what if the ejection mechanism was not the typical gravitational perturbation from giant planets, but something more exotic, such as a close stellar encounter or a catastrophic dynamical instability that reshaped the entire system? Such events could explain both the ejection and the extensive fragmentation. What if the comet's unusual characteristics and its accompanying cloud reflected planetary formation conditions radically different from those of our own system, perhaps around a binary star, or within an environment whose chemistry was significantly altered by a prior astronomical event? Nevertheless, current observations indicate that, regardless of its specific stellar system of origin, 3I Atlas most likely formed in a planetary formation environment fundamentally similar to our own. The presence of volatile ices and organic compounds akin to those found in solar system comets suggests a certain universality in planetary formation processes, though with significant variations in specific conditions and resulting chemistry. The extraordinary swarm accompanying 3I Atlas raises fundamental questions about the physical mechanisms capable of fragmenting a cometary body into thousands of pieces. The chemical composition of 3I Atlas provides invaluable information about the diversity of conditions in distant planetary systems. Spectroscopic analyses have revealed a fascinating mixture of both familiar and exotic compounds, offering a window into the chemistry that operated in its system of origin. Data from the James Webb Space Telescope have identified numerous volatile compounds sublimating from a nucleus, including water, carbon monoxide, carbon dioxide, methane, ammonia, and complex organic molecules, such as methanol and formaldehyde. This chemical diversity is comparable to that observed in solar system comets, suggesting a certain universality in the building blocks of planetary systems. However, the relative proportions of these compounds differ significantly from those found in local comets. Particularly notable is the unusually high abundance of molecular nitrogen and nitrogen-bearing compounds, including hydrogen cyanide and ammonia, which exceed typical solar system comet ratios by a factor of 2 to 5. This nitrogen signature could indicate formation in a colder region of the protoplanetary disk, or in a disk with a higher initial nitrogen content. Isotopic measurements have provided additional fascinating clues. The deuterium to hydrogen ratio in the water emitted by 3I Atlas is approximately 30% lower than the average value in solar system comets, while the carbon-13 to carbon-12 ratio is slightly higher. These isotopic differences definitively confirm that the object formed in another stellar system with a distinct evolutionary history. Particularly intriguing is the detection of several complex organic compounds, including amino acids such as glycine, alanine, and possibly valine. Although these compounds have been detected previously in solar system comets and meteorites, their abundance in 3I Atlas is remarkably higher, suggesting chemically fertile conditions in its parent system, potentially relevant to considerations of habitability and the origins of life. The cloud fragments show subtle but significant compositional variations among different groups, indicating chemical heterogeneity within the original body. Some families exhibit higher concentrations of sulfur-bearing compounds, while others are relatively enriched in organic molecules, possibly reflecting different formation regions within the original protoplanetary disk. When we consider the broader meaning of these interstellar chemical messengers, we find ourselves exploring the frontiers of comparative astrochemistry. Each molecule, each isotopic ratio, each compositional anomaly tells part of the story of another planetary system, one we will never be able to visit directly. What if the unusual chemical signatures of 3I Atlas reflected not only differences in formation conditions, but also subsequent chemical evolution during its interstellar journey? Could cosmic radiation have catalyzed exotic chemical reactions over millions of years of exposure, creating compounds that would not naturally form in protoplanetary environments? And what if the elevated abundance of complex organic compounds indicated that the ingredients for prebiotic chemistry are even more common in the galaxy than previously believed? Could this interstellar visitor be offering us clues about the prevalence of the chemical components necessary for life? What if the chemical heterogeneity among different cloud fragments were effectively providing us with multiple samples from different regions of the same planetary system, allowing us to reconstruct the chemical structure of its protoplanetary disk in a level of detail impossible to achieve for distant systems? Subscribe to the channel so you don't miss more content about these fascinating mysteries of the universe. Nevertheless, current observations indicate that although 3I Atlas exhibits distinctive compositional differences from solar system comets, it shares enough fundamental similarities to suggest that the chemical processes operating during its formation are variations of the same basic principles that govern the birth of our own system. The chemistry of 3I Atlas is exotic but recognizable, different, yet interpretable within our current theoretical frameworks of planetary formation. The discovery of 3I Atlas and its extraordinary cloud of fragments represents a turning point in our understanding of interstellar objects and, by extension, of the formation and evolution of planetary systems throughout our galaxy. The scientific implications of this exceptional visitor extend into multiple fields of astrophysics. The long journey of 3I Atlas through interstellar space has turned this comet into a unique witness to the conditions prevailing in the void between the stars, like a detector that has been continuously exposed for millions of years. Its surface and current composition contain invaluable information about the interstellar medium, that faint yet vast ocean of gas, dust, and radiation that constitutes most of our galaxy's volume. High-resolution spectroscopic observations have detected the presence of a fine layer of material deposited on the comet's surface that differs chemically from the underlying nucleus. This interstellar patina contains compounds enriched in heavy elements, particularly iron, nickel, and platinum group elements, consistent with the gradual accretion of interstellar dust during its cosmic voyage. Fascinatingly, the comet's surface shows evidence of space weathering. Tiny craters and abrasive structures caused by impacts with interstellar dust grains traveling at relative velocities of tens of kilometers per second. Statistical analysis of these surface features provides direct information about the density and size distribution of interstellar dust along its path, data impossible to obtain through conventional remote observations. The comet's outgassing patterns reveal significant differences between volatile materials in its surface layers versus deeper regions, possibly reflecting chemical alteration caused by cosmic radiation. The outer layers show a marked depletion of hydrogen and a relative enrichment in deuterium, consistent with selective photodissociation driven by interstellar ultraviolet radiation over prolonged periods. Particularly intriguing is the detection of complex organic compounds that appear to have formed or been modified during the interstellar journey, including polycyclic aromatic hydrocarbons with unusual structures and complex nitrogen-bearing organic molecules. These compounds may result from surface reactions catalyzed by cosmic rays, demonstrating that interstellar chemistry can produce molecules of significant complexity even under the extremely diffuse conditions of the space between stars. Polarimetric studies of the coma have provided insights into the interstellar magnetic field, revealing preferential alignments of dust particles that suggest interaction with the weak yet persistent galactic magnetic field. These measurements represent one of the first direct detections of the geometry of the interstellar magnetic field at small scales. When we consider 3i Atlas as a cosmic laboratory that has been collecting data for millions of years, we begin to appreciate the extraordinary value of this visitor as a probe with the interstellar medium. Unlike our conventional observations, necessarily limited in time and constrained by instrumental sensitivity, this comet has integrated the cumulative influence of its environment over geological timescales. What if we could read the complete story of 3i Atlas's interstellar journey in the layers of its surface, as geologists read Earth's history in sedimentary strata? What would it tell us about variations in density, composition, and radiation conditions across the regions of space it has traversed? What if some of the exotic chemical compounds detected on its surface were unique product reactions that can only occur during extremely prolonged exposure to interstellar conditions, processes impossible to reproduce in terrestrial laboratories or even to observe in conventional space missions? What if the interactions between the fragmented cloud and the interstellar medium could provide us with information about small-scale turbulence and the filamentary structure of interstellar gas? Fundamental properties for understanding star formation, but extraordinarily difficult to measure directly. Nevertheless, current observations indicate that although 3i Atlas has been undeniably modified by its interstellar journey, it largely preserves the fundamental characteristics of its system of origin. The surface alteration, though significant for our understanding of the interstellar medium, represents only a small fraction of the object's total mass. In its silent passage through our solar system, 3i Atlas whispers secrets from distant regions of our galaxy, places we have never visited and may never reach. As an uninvited ambassador from another stellar system, every aspect of this comet and its accompanying cloud constitutes an encoded message about the diversity of the cosmos and the processes operating beyond our immediate solar neighborhood. The structures present in the fragment cloud, with their complex patterns and non-random distributions, represent a physical record of events that occurred millions of years ago around another star. The position of each fragment within the cloud, its size, relative velocity, and composition, contains information about the forces and processes that created this extraordinary formation. The isotopes trapped within the comet's ancient ices provide clues to the composition of the protoplanetary nebula in which 3i Atlas formed, offering us a glimpse into the chemical conditions of another planetary cradle. The ratios of deuterium, nitrogen-15, and carbon-13 reveal aspects of the environment in which these primordial materials were forged, potentially including information about the previous stellar generation that enriched that region of the galaxy. The specific morphology of the main nucleus, with its craters, fractures, and surface features, record an evolutionary history completely independent of any object in our solar system, offering a valuable counterpoint to our theories of cometary evolution. Every surface irregularity tells part of the story of this interstellar traveler, from its initial formation to the events that sent it on its trajectory toward us. The complex organic compounds detected in its coma, some with structures not previously observed in solar system objects, expand our catalog of naturally occurring prebiotic chemistry in the galaxy. Each exotic molecule represents a new entry in the dictionary of cosmic chemistry, potentially relevant to our understanding of how chemical complexity, and possibly life, could emerge in diverse planetary environments. The coherence of the cloud throughout its long interstellar journey provides insight into the dynamic stability of such structures over vast timescales, offering clues about how matter maintains organization amid the apparent chaos of intergalactic space. Each measurement of fragment interactions contributes to our understanding of n-body dynamics under conditions impossible to reproduce experimentally. Share your thoughts on these questions and join the discussion with the community. When we consider 3i Atlas as a cosmic message, a time capsule from another planetary system, we face the reality that we are interpreting a text written in a language we only partially understand. The whispers of this cosmic ambassador are encoded in a dialect formed by universal physical and chemical processes, yet manifest under specific conditions we can only infer indirectly. What if we could fully read the physical record preserved within 3I Atlas, deciphering its entire history from its initial condensation in a protoplanetary disk to its arrival in our system? What might it tell us about the diversity of planetary systems in the galaxy and the processes that form them? What if the chemical and structural complexity we observe in this interstellar visitor were indicative of far greater richness and diversity in planetary formation processes than our solar system? Limited perspective has so far suggested. Could our current worldview be as provincial as that of the ancients who once believed Earth was the center of the universe? And what if, hidden within the seemingly random characteristics of this comet and its cloud, we were missing patterns that could reveal new fundamental aspects of small body physics? How do we distinguish between cosmic noise and meaningful signal when we have only a single sample of a potentially diverse phenomenon? In an extremely speculative scenario, what if some of the patterns in the cloud were not entirely explainable by known natural processes? How will we recognize evidence of artificial manipulation in an interstellar object if we were to encounter it? This purely imaginative exercise reminds us of the limits of our certainties and the importance of keeping an open mind in the face of the truly unknown. Nevertheless, current observations indicate that, though extraordinary in many respects, 3I Atlas appears to be the product of natural processes of planetary formation and evolution, possibly under different but fundamentally similar conditions to those that operated in our own solar system. The whispers we hear from this cosmic messenger confirm the universality of physical laws across the galaxy while revealing the rich diversity of their specific manifestations in different stellar systems. The interstellar comet 3I Atlas represents one of the most significant astronomical discoveries of our era. Its nature as a visitor from another stellar system, unequivocally confirmed by its hyperbolic orbit with an eccentricity greater than 1, makes it only the third confirmed interstellar object after 1I/Oumuamua and 2I/Borisov. However, what definitively distinguishes 3I Atlas is an extraordinary cloud of approximately 10,000 discrete objects accompanying it in coherent formation, an unprecedented phenomenon among both interstellar objects and solar system comets. Detailed observations have revealed a cometary nucleus with physical and chemical characteristics that, while familiar in their basic aspects, differ significantly from local comets in isotopic ratios, abundance of specific compounds, and dynamic behavior. The escorting fragment cloud displays structural and compositional complexity that defies simple explanations, suggesting multiple fragmentation events and a rich, complex evolutionary history. Beyond its immediate scientific value, 3I Atlas invites us to profound reflection on our place in the cosmos. This messenger from another stellar system reminds us that our solar system does not exist in isolation, but rather as part of a galactic ecosystem where matter and information constantly flow between systems separated by vast distances. The arrival of this interstellar traveler vividly illustrates the fundamental interconnectedness of all planetary systems within our galaxy. The atoms that make up 3I Atlas were forged in the same types of stellar processes that produce the elements of our own system. They traveled through the interstellar medium, became incorporated into a distant planetary system, were processed within its protoplanetary disk, and were eventually expelled back into interstellar space before their chance encounter with our solar system. This cosmic cycle of matter links us physically and tangibly to distant regions of our galaxy. The sheer statistical improbability of our opportunity to observe this extraordinary phenomenon reminds us both of the limits of our perspective and the astonishing fortune of existing at a moment and place that allow us to contemplate such cosmic wonders. Each fragment of this interstellar cloud represents a window into another world, a world we will never visit directly, yet whose existence we can infer through these silent ambassadors. If you're enjoying this content, Don't forget to like, subscribe, and activate the notification bell to stay updated on our upcoming videos exploring the mysteries of the universe. In the silence of deep space, 3I Atlas continues its eternal journey, indifferent to our observations, theories, and speculations. It arrived from the depths of the cosmos, carrying secrets from places we will never directly know. It briefly crossed our path and now drifts away, continuing a voyage that began millions of years before our species existed and will persist long after we are gone. Like a cosmic whisper, this traveler has told us stories from another time, another place, another planetary cradle. Within every fragment of its cloud travels an echo of processes that once operated around a distant star. On the skies we will never see, yet governed by the same fundamental physical laws that shape our own cosmic home. In our brief encounter with this stellar emissary, we have glimpsed the vastness and diversity of the cosmos, reminding us that we are privileged observers in an immense, ancient universe, filled with wonders we are only beginning to comprehend. Each interstellar comet, each fragment from another world, invites us to expand our horizons and recognize our fundamental connection to the greater cosmic tapestry. As you depart our system, 3I Atlas, carrying the secrets of your origin, you leave us enriched by your visit. In your silent passage, you have reminded us that we are part of a broader cosmic conversation, where messages travel not at the speed of light, but at the patient cadence of gravitation, across ends of time and abysses of space. Perhaps someday, in a distant future, another observer around another star will witness your passage with the same awe we feel now, united across time by the same shared curiosity about the mysteries of the universe. Thank you for joining us on this journey through the cosmos. Share this video with other space enthusiasts, and tell us in the comments which other astronomical mysteries you'd like us to explore. See you in the next video.